OpenCV. I'm giving a talk on open source for social good as part of this conference, and I'm going to be using the open source computer vision library as an example all along. These are two barcodes that give links to OpenCV organizations. Okay, so open source for social good. Open source, if you properly understood, is a lot more than code. It's actually a kind of philosophy or movement, and it's really it aims long. It aims at really reorganizing the institutions of humanities, like in economics, politics, institutions. The code is just the start, and already many things are happening in it, like open source hardware, and anyone can fix. So the chief thing open source does is it speeds up the pace of technology, because people have access to this. And in so doing, it is a competitive disadvantage to those opening source. If I kept OpenCV to myself, I could have a company, but it's really, the people who are doing this are playing a longer game, because it's supporting a lot more than that. It's supporting a kind of social order where order emerges. You can think of the state of nature. There's no control, but it has order because of the dynamics. So that's what open source is trying to do. Because it's available, it allows for people to do things, but it also it makes this order resistant to what kills most order, and that is winner take all, when too much power gets into someone's hand. With open source, it's difficult for someone to dominate, because everybody has access to the foundations. And that's in technology and everything else, but so it's a very long game. They don't expect open source to take over world order in my lifetime, or even maybe in the lifetime of nations. But it's really looking beyond, because it's accelerating technology, and at least my vision is that there will come like intelligences that humanity will create, AIs and robots, and open source is really looking also for them, that they'll, by having the source code, no corporation or government, that they control their own destiny. So what comes after us, including us, will have this open substrate from which to build from, that belongs to everyone and no one. So that's the long game of open source. So I'm going to be using the example of OpenCV, which is a very micro part of all of this. It's the open source computer vision library. So what is it? It started 20 years ago as an open source computer vision library. It's now it's mature. It's 20 years old, and it has a very wide reach. We think with Python we're getting 1 to 2 million downloads a week through pip install and other things, but we've gotten tens of millions of downloads formally on SourceForge, and we get about 10,000 downloads a week from GitHub. It doesn't track total downloads, and it has a wide developer community. So we have over 10,000 patches now. We get about 5 new patches from the community a day. So that's OpenCV. Again, how did it start? It kind of started in this movement for social good. Like 20 years ago, I joined Intel Research, and they told me they wanted me to publish, to put their research lab on to bolster its reputation. And really, Intel wanted this lab to boost the need for computer performance. So back then, it could already run a spreadsheet, and they were wondering, new, more powerful processors were coming. What would they do? Of course, this is somewhat of a joke now. The internet happened, images happen, but my idea back then is, well, computer vision is a large need of computation. So I visited, I went around really the world looking at computer vision labs, And back then, 20 years ago, I found that everyone was writing their own code, which we call like reinventing the algorithms. A lot of bugs, hard to know if they re-implemented it right or wrong. So the scientific papers were hard to check because you could never know, did you implement their algorithm right and beat it, or did you make a bug? And so you didn't beat it, and you couldn't, you know, science is based on reproducibility, and you couldn't reproduce anything. So these were some of the problems. The coding practices were terrible all around the world. They still are to some extent, but the field back then, nothing worked very well in computer vision. So I decided my focus when I joined, I wasn't told to do this, but I would create this an open platform to solve these problems, like that people were reinventing algorithms. I could give them a platform from which everybody would start. It would also make it easier to read papers because you knew they were built on some core components, and you knew those components were debugged. It's also, you know, for business and whatever, I wanted it free for them because I wanted to accelerate the field, not just research. Like, I wanted people to deploy things. And again, like I've said, like, to advance technology for humanity, the fact that these algorithms were out there made it easier for other people to learn. And so you know, OpenCV was a few times in life when you set out with a plan, does that plan succeed? So OpenCV is one example from my life that all these goals have, you know, come to being. And now computer vision is a robust field. The library is well used, and it forms a basis for algorithms. So let's move on to a tour of OpenCV. So OpenCV, at a glance, it's a large collection of computer vision algorithms and techniques. So it spans image processing, basic things like, you know, eroding images and isolating things. It does transforms, so rotations, perspectives. It does fitting, you know, shapes to shapes. There's a lot of support for that. A big section moving across is optical flow, tracking and registering to a scene. Segmentation on the right, we can break up the scene into parts, and there's something semantic segmentation, can label all the pixels in the scene. Going bottom left, we see calibration. There's a lot of support for this, and this is, you know, how to adjust the parameters inside, they call it intrinsics, of a camera, and then extrinsics, how to relate this sensor to the world or to other sensors or other cameras. We also have a lot, you know, moving across support for feature tracking and visual SLAM. SLAM is simultaneous localization and mapping. So learning the world as you're moving around in it and being able to localize yourself again in the maps, something humans do easily, but, you know, it took a long time to get computers to do this. In the middle, we have this RGBD, that's color plus depth. So we're having increasing support for that. And then on the right, well, on the far right, we have computational photography. These are effects you can get in imaging and video. And so there's a lot of things that are fun, but close to that is something we've really concentrated on, is deep learning, which is taken over the field. It's the AI. And so the library supports deep learning models, the inference, running them seamlessly and optimized on basically all architectures that are out there. Okay, so moving on, here's the history. It's, you know, I joined in 1998 in Intel and started this library, which launched in beta in 2000 at the Computer Vision and Pattern Recognition Conference, one of the biggest vision conferences in 2000. And, you know, 5 years later, I had joined the DARPA Grand Challenge, which was the race of robot cars, unmanned cars across the desert. And so we won that, and I was on the Stanford team, Stanley, using OpenCV and LiDAR and other things. We won that challenge, and that really kicked off this autonomous driving industry. Ironically, Waymo now is what this has become. So Google basically bought that team, and it's now become Waymo, their self-driving car. Ironically, it's a kilometer from my house, so I see robots every single day, and I'm wondering, like, if they kill me, it will be like killing their grandfather. But so far, no collisions. In 2006, the release 1.0 was out, and then moving along, we moved to this place called Willow Garage. It was an incubator, and they supported OpenCV, so we turned OpenCV to C++, and we got the 2.0 release with Python. We moved it to GitHub, which is one of the standard repositories for open source code, where it is today. And you know, moving on, there was a team of ITZYs that helped in Russia. And so Intel bought them, and they're still working on the library part of the team, but it's also part of OpenVINO. And then in 2016, this DNN module, the Deep Neural Network module started. You know, now we've modernized it to Modern C, and I've revamped the distributed development, so it's now worldwide. We have supported people working on it worldwide. There's 2 teams in Russia. I'll go over this. And we're working towards release 5.0 at the end of the year, which is bringing it up to C++ 14 standard and adding a lot of things, which I'll talk about. So, you know, this year, a lot of stuff has happened during the pandemic. 20th anniversary is going. Like I said, the release is planned at the end of the year. We switched. There's an open source library that allows business and commercial and research use. We switched. It's the same kind of license, but it's Apache 2. What Apache 2 does is it offers more defense against patent attacks. So we switched to that, but for most users, they don't care. It's a completely open for business or a research license. We added a lot of new things this year. We also came out with courseware that you can see on our main site. We're doing development partnerships, so we have smart cameras coming out, and there's a store. It's going online as of tomorrow, for actually today. Sorry, selling these courses and cameras, and this will get bigger. This is a Black Friday sale. Okay, and then I'd mentioned a key part is we've really been working a lot on this deep neural network library, because that's becoming a lot of vision. So we run, OpenCV serves as pre and post processing for deep nets, and for example, it's used in Google's Media Pipe. But we run these things, any model produced by PyTorch, TensorFlow, Caffe, Darknet, ONNX, we run them in OpenCV optimally across this architectures, Movidius, NVIDIA, ARM, FPGA, and RISC-V. Like I said, we've been also putting a lot of work into ARM because it's becoming a ubiquitous architecture. So there's now an optimized version of OpenCV. We recently got in a huge server that's putting OpenCV through all the tests and whatever to keep it stable on ARM. We're also booting up the RISC-V implementations for the same thing. This is going, you know, OpenCV on the edge, very low power. Other things like we've added bindings for C and Swift, and it doesn't say Julia. Like I said, we're supporting more and more deep neural network topology. So if you're into this, you know, YOLO, FlowNet, many kind of segmentation architectures, and better support, easier to convert models over to OpenCV. Once you run the inference, you can run them anywhere. So it makes it very convenient. And I've been running this thing to add color calibration. So there'll be full color calibration in OpenCV. This shows this Google Summer of Code runs internships, and we're trying to raise money to run a OpenCV internships. But basically, these support interns around the world. There are several people in Russia who worked with us, and they work at home, and they're paid with a mentor. And some of the things that came out of this summer were Julia bindings, JavaScript, so the OpenCV runs natively in browsers. I did this Macbeth chart detector with an Indian student, and we got a donation from a guy at Huawei to do color correction. And so all that's coming in. We got very state-of-the-art tracking. We've put in state-of-the-art RANSAC algorithms, so this is helping calibration and geometric algorithms much faster than the existing ones, and those will become the default in 5.0. We have a lot of state-of-the-art text detection and recognition, and many demos of how to run this on the web. At the bottom, you'll see Connect Fusion. So when you get a depth sensor, move it around, you average onto surfaces, and you get in the bottom center a smooth depth representation. We're now doing this at scale from a helicopter to create accurate depth models of a large area with a company. So I said, 5.0 is coming out. It'll move to C++ 14. A much better Python API is coming. It's Pythonic, more Pythonic. We have a full-scale 3D model, so like really addressing this interface between 2D sensors, the camera, and 3D LiDAR and point clouds. So we'll support that. Many improvements in the deep neural network library, and moving on down, I already mentioned ARM support. We will support audio and video natively also. And then I'm doing a lot of work in, with others in calibration, both color and geometric calibration. So we'll have improvements on that. Again, I talked about growing development, so I've revamped the organizations. And so there exists in California people working on OpenCV, but going down in Russia, in Nizhny Novgorod, there's two groups, one at Intel and one that I support. 3 developers that are just paid for by the organization that are full-time. One is full-time on pulling in the pull requests, and 2 others will start helping with calibration. In Shenzhen, China, we have a growing team, and with industrial partners. Right now, they're chiefly working on ARM optimization. And then there's a community around the world, like I said. Every day we get in 2 to 5 patches from hundreds of people who contribute. Okay, so I'd set up this board, an advisory board, OpenCV. So this is, you can just take a quick look around the world. There's US, Russia, China, France, Italy, Spain, people who are on our technical advisory board. We discuss algorithms and what the direction should be. And finally, in the OpenCV tour, just this overview. We're on GitHub, and it's well liked. One of the favorite projects there, one of the biggest projects there. We get 1 to 2 million people installing through pip or other techniques a week. It's the favorite embedded vision library, and it's the largest vision library in the world, also largest in usage. Okay, so we had set up to further serve this because getting more and more contracting requests or implementation. So we have the org, and that's supporting development of the library. We also have a for-profit that's developing partnerships. I'll show you for a smart camera. It does contracting work for people who need these things to, implementations or tunings or whatever. And we're also producing courseware, to help spread, computer vision knowledge. And so this is just going through the OpenCV.ai. We're probably expanding, but many of the people are in Russia, mostly Nizhny Novgorod and Moscow. But we also have a growing number in India and some in the US that are joining in these contracting projects. So we have some mathematical experts, especially in geometric and deep net algorithm in the US, who are joining on some projects. I think, yeah, I've already gone over. There's courseware. It's on sale today, but these are very well done courseware. It's introducing you to computer vision, then how to use OpenCV and you know, the deep nets and all the stuff, and then how to train them using PyTorch. So then they're done very well by a very good instructor. I had already mentioned this OpenCV toolkit, and you know, there's a depth sensor. This is selling for about $200. The other one is about half that price, but it's a depth and RGB sensor. It also runs AI algorithms on board, so all this is done on board the chip. It's called the OAK-D, or the OpenCV AI Kit. And I just show here some of the things it does: people detection, pose detection, object detection, tracking, and many other things. And we're building this into products. So really doing this to get the price down, because the more volume, the cheaper it gets, and then the more things you can do with it. Okay, some use examples, which I'll go through quickly. These are OpenCV used in the real world. So in this case, it's on an FPGA, it's a people detection, sports training, face recognition. I had mentioned the 3D understanding, augmented reality. We can do it, you know, gesture. Doing some medical work. This is a tumor segmentation, you know, that we did for a challenge. But real medical work, this is by amplifying the signals in a regular camera. You can see blood flow through the skin, and this is, you know, will be useful in surgery to see that your blood flow does not diminish too much. When you take an anesthetic, your blood flow diminishes on the skin. You can really see it through this thing, and it's important. They don't yet actually track this. It's the surgeon and anesthesiologist who do it through experience, but here you can visualize it. Again, like reading of pulse and breathing from a distance, and this is like it came with COVID. We're also doing this COVID app that's reading an at-home test, so that the humans don't, you know, you put some sample into a little cartridge, and the computer reads it rather than the human. So the computer knows to wait for 15 minutes with your cell phone, and then it reads the COVID test. So we're hoping that's under emergency FDA approval. We're hoping that'll come out and help testing, at-home testing. We're doing a lot of stuff with people in ag tech. So those are some things. I mentioned text recognition a while. In film and broadcast, I was part of this company that did a lot of effects in film and broadcast, tracking people, segmentation, car tracking. So they get a different car and they overlay it with a new model that they don't want to show publicly yet. And I can show some of this film broadcasting. This is an example of OpenCV's use in film and broadcast. So we're tracking points in the scene so that we can insert graphics and have them look like they're on the field. And here was footage from a Super Bowl stadium that we later overlaid graphically. And we also have some examples of studio film running around the scene, and we're inserting graphics and accurately tracking. OpenCV and robotics. So just like when OpenCV started, the state of robotics wasn't very robust. It isn't very robust. It's slow. There's not a lot of smart robots that are actually out there. And everybody, they get teams, companies get teams, they're re-implementing it. They think they're the secret ones. And I really want to get these pieces together so people just work on their applications rather than everybody re-implementing SLAM and these other pieces. So, you know, that's what we hope to work for. This is a scene from Industrial Perception, a company I worked on where we used OpenCV and other techniques to create a truck unloader And here, just for fun, we had it throw the boxes, but it was actually putting them down on a conveyor belt. This is OpenCV helping start off the autonomous driving industry, and this is a video showing some highlights from winning the first autonomous driving challenge. We won $2 million. This is a scene in the DARPA Grand Challenge where autonomous driving really got its start. OpenCV was used in this. So there's Boss, the first car out. They only raced by time, so each one was released separately. You know, this is Stanley starting the car I worked on that won the challenge. Over here was a aerial map where the cars were tracked. So this was about a 7-8 hour race across the desert. This is where Stanley passed the CMU car, Boss. And so you see it in the image, and then LiDAR. This is Stanley coming down a mountain pass, so there was a steep cliff on this side, and after that there was a plane towards the end of this race, and so in 7 hours it started heading towards the finish line, which you see here, and this race, so 7 hours autonomous across the desert, and this really set off the autonomous driving industry. Other uses that can serve vehicles, we have the Zoom-like background segmentation, so free flow. So this is two other things in OpenCV. One is this freeform background segmentation that we license above, and then there's semantic segmentation of cars, the ground, buildings, trees, sky, all pixels below. And this is an example of optical flow and reconstruction, showing it in the video in AgTech. This is an example of an AgTech of tracking the optical flow of points in an agricultural field, and then using wheel odometry and the track points to reconstruct the 3D model that you see on the right. So this is just from optical flow and wheel odometry. This is an example of state-of-the-art object tracker in OpenCV, so soccer balls, motorcycles, airplanes, I think we get cars, and then animals. So it's quite a robust tracker. I think people will be next, and so this is quite a useful algorithm. This is OpenCV using car tracking and speed detection, so it's counting on the left and it's estimating the speed of cars on the right. Okay, so I wanted to bring this together a bit on, like, what are we accelerating? And robotics teaches us about the mind, how to make a mind, and this is like one of the ultimate goals of AI. And so this slide is a little bit about Stanley's brain. You can see it gets many sensing sources up there on left. It gets lasers and odometry and GPS, and it fuses it in a camera. So the lasers tell the camera, this is good, flat land, extend it. You can see in the middle that red is the segmenting the road. And this all becomes fused. This is how Stanley, the robot car, worked. In its mind, it ends up in this model where all this information is fused about where it is. The red is bad things, the white is good flat land, and the gray is I don't know. It also has its direction of gravity. And then Stanley went through physics simulations of how it could drive through what it saw in a real physics simulator so that it doesn't turn the car over. That was Stanley, the mind of this robot. Here is an example of how would you communicate other things to such a mind? The mind is really programmed by emotions, so that little car in this thing, lower left, its emotion, what its goals were, it was to follow a set of GPS waypoints to travel this road as fast as it can. Again, it saw white is the good area, gray it doesn't know, and red is bad things. And so let's say you're going to try to communicate Dostoevsky's Crime and Punishment, the first part of the plot, to this robot. This is its brain. How would you do that? Because this is all Stanley knows. And what you might say is, well, the hero is the person in the story is impetuous, like he decides to murder someone. But that's a risky, rash decision. So normally Stanley would follow the safe white going around GPS waypoints. But this, the crime and punishment guy, they're taking a shortcut, and it's risky. Eventually, by taking these risks, it will crash. But this is how you're going to explain to Stanley what Crime and Punishment, the novel, is about. To its brain, it's about some car that goes over the gray area, risking, and that's the only metaphor it has to think with. So that's its brain. We aren't so different here in our reality. For instance, I'm using the analogy of a computer screen, and on your computer screen, here's a garbage can, and I'll tell you, it's not a real garbage can. And you go, yes, I'm a physicist. It's made out of quantum called pixels. And I go, no, really, it just represents something in the computer operating system. The only thing you have to know is it's a causal interface. That means if you drag something into that trash can, it will actually be destroyed. But there's no real trash can, right? That's simply an interface to your reality. So I'm trying to make the claim here that the underlying reality, the von Neumann architecture, is very different from your graphical interface, and yet the graphical interface is a causal interface to the underlying reality. I'm saying, like, humans are not so different. We get these perceptions and we simulate a world. You'll notice houses on a street are both the same size and different size all at once, but as we simulate it, it makes sense to us. So I try to use the simulated world we're living in as with a question, what is beyond the sky, or what is below your desk? And it's obviously what's beyond the sky is the inner surface of your skull, because you're not out there, you're inside your brain, right? Perceiving through a model, a causal model of reality. And this is the slide that needs to be replaced. Talking through this slide, well, we can do this later. This is change blindness. I'm showing that human perception isn't complete, but has. So in this, this is a video. I'm going to pause here. This is an illusion called change detection. So a major part of this image is changing. Let's see if you can find it. It's the shadow under the helicopter. So this shows that your mind doesn't really represent the world. It represents a causal model of the world. This shows on the left, like, perception isn't real. Those two squares look very different color, but on the right, I've isolated them. They're the same shade of gray. So again, perception isn't so real. These strawberries look red. There is no red in the scene. They're gray. It's just context, and you can see the gray I've isolated on the left. In this, if it works for you, you will see wherever you're not looking, there's a motion, but there is no motion. So our system is a causal interface that can be fooled. And so these are hints about how to build a brain, that brains need a causal model, and so, you know, that itself will be an advance. And you know, I'm kind of saying this here, ending with the new video put out, you know, to get humanity off the planet and advance robotics, which I think is for our social good. This is the end, or I went over time.